Okay. So, a reduction in shunt capacitance relative to the capacitance of each unit, this is one way. This can be done only by increasing the length of the cross arm, but you cannot increase the length of the cross arm because cost is a major factor, right. But due to the limitation of mechanical strength and cost of towers, right, the value of k cannot be reduced to less than 0.1. So, you cannot make it that k value, that means this value 0 to 1, less than 0.1, right. Now, that is why one method is there, that is called capacitance grading. So, this way insulator efficiency can be, string efficiency can be increased. Capacitance grading means an increase in the capacitance of each unit from the tower end towards the line end, right. So, you increase the capacitor from the tower end towards the line end. So, that is called capacitance grading. Theoretically, the voltages across the different units can be made exactly equal by correct capacitance grading. If you can go for a correct capacitance grading, then voltage across each unit, there are so many units in each string, it can be made equal, but this is seldom done because it implies that all the insulator discs are of different from another. I mean, if you try to make it, then you will find insulator different disc will be of different types. I mean, so that one will be different from another. So, in this case, this involves maintaining pairs of all variety of insulator discs. I mean, all type of insulator discs are required, right, which is contrary to the tendency of standardization, since only a few types are possible. So, only few types of insulator discs are possible. So, in reality it is not possible to make all the voltage, that voltage across the different units can be made exactly equal. So, voltage across each string, it is not possible to maintain exactly the same voltage, right. So, if you try to make it, then that different units will be of different sizes and may not be available all different different sizes, except some standardized size is there. Therefore, the value of V n can be found by your what you call this one, sorry. Therefore, one method is there, one method is there, that is called static shielding. This figure 1 actually, now look at this figure 1 is static shielding. So, here it is, this is your cross arm, this is actually your cross arm, and this is your support, that is the tower, this is your support, right. So, what is that? This is called static shielding. What is done actually? This method uses a large metal ring surrounding the bottom unit, here it is the bottom unit here, a large metal ring surrounding the your what you call bottom unit and connected to the line. If you look at the transmission tower in many places, this thing also you will observe. This is capacitance grading, this thing also you will observe, right. That means, this method uses a large metal ring surrounding the bottom unit and connected to the line. So, this ring known as a grading ring, and it introduces capacitances between different joints and line. This has the different this has the effect of increasing the effective capacitance of bottom units. So, this has the effect that it will increase the capacitance of the bottom units. So, this figure 11, it is seen that, look at that, it is seen that if the value of S n can be adjusted, that means this value, if this S n value, this is the capacitance value, I have put S n, if S n can be adjusted by adjusting the shape of the ring, that means the ring you have to adjust, this ring you have to adjust the shape of the ring, such that if you can make that your I n dash is equal to I n, if you make I n dash is equal to I n, then all this string, all this unit, you will find the same I current is flowing, but in reality it is not possible, then voltage will be equal, right. If you can adjust this S n value such that your I n will be I n dash, equal current, then if you apply Kirchhoff's first law here, then it will find I n plus 1 is equal to I n, that every unit you will find the same current, but which is not possible, So, it is seen that if the value of the S n can be adjusted, then this one or the voltage across nth unit would be equal, nth and n plus 1th unit will be equal, that means n and nth plus 1 unit voltage will be equal, which is not possible actually, but this capacitance grading is there. If you look at any transmission tower, you will find this is there, right. Though the shape of the ring can never be adjusted, it is not possible actually, though the shape of the ring can never be so adjusted as to give perfectly equal your distributions, considerable improvement are still possible. Although you cannot make I n is equal to I n dash, but by adjusting this you can try to improve that your voltage distribution, right. So, every insulator string is provided with an arcing horn at the lower end and at the line end. If you observe the insulator, you will find on the top and bottom of the top and bottom, right, is provided with an arcing horn at the tower end, on the tower side and the line end, so that the event of insulator flashover, the arc may take the path between the horns and stay clear of the insulator string. So, on the top and the bottom you will find some arc horn in there. If flashover takes place, it will be through that too only, and somehow it will bypass the your what you call that insulator string. So, static shielding is achieved. Static shielding is achieved by changing the arcing horn at the line end to a grading ring. So, static shielding can be possible by changing the arcing horn, right, at the line end to a grading ring. So, this is your line end, this is your line end. That means, this way it is your what you call it is possible. So, this is later we are not deriving this your what you call this much formula or anything for that, but when we will take the numericals on this, at that time we will try to solve the numerical, but these are one method and commonly used also, that your static shielding, right. So, next come to the example. That capacitance grading other thing, if possible we will take the problem. Now, question is that example 1 you come, and actually insulator topic is quite easy for you, right, compared to many other difficult topics. So, just you have to little bit concentrate and that is all. So, an insulator string, the problem is 66 kV line has 4 discs, that means 4 units are there. The shunt capacitance between each joint and metal work is 10% of the capacitance of each disc. Find the voltage across the different discs and string efficiency. So, it is says that 4 discs are there. So, 4 capacitance 1, 2, 3, 4 C, 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 and the shunt capacitance between each joint and metal work is 10%, right. So, that means your this is your 0.1 C, that is K is equal to 0.1 actually, 0.1 C, 0.1 C and 0.1 C, right. If you have a 4 disc means 3 such shunt capacitance thing will come. For this from 1, this is from 1, this is from 1, and nothing will be there because it is a line actually, line is connected here, conductor is connected here. So, if you have n number of units in the string, that means you have n minus 1 number of this shunt capacitance, right. So, the arrangement is shown in figure, this is figure example 1. If the capacitance of each unit is C, then each shunt capacitance equal to 0.1 C. Applying KCL to different junction, we have you have to apply KCL equation. See, this is P, this is Q and this is R, these 3 points are taken. So, look at this your your this thing at junction P, you can write your omega, this is your at P point, that omega C your the way it has been made, it is voltage, this is V1, this is V2, this is V3 and this is V4. Total is V1 plus V2 plus V3 plus V4, up to this is V1 plus V2 plus V3 plus V4, right. So, at junction P, if you write at junction P this equation, it will be, this is coming from that same equation omega C V2, that means your this current is this Q to P, this current is omega C V2 is equal to the current here, current in this branch omega C V1, omega is taken common out. So, in bracket omega C V1 plus omega into K C V1. I mean if you have any understanding problem, I am just drawing one for you. take the first one, this is your your cross arm, this is cross arm, and this is your supporting tower. This is your first one I am making for you, this one, and this is your 0.1 C, and this is C, and this is C. This point is P, this point is P. Suppose current here, for example, say it is your I2, current here is say it here I1 dash, and this current is your what you call I1. Therefore, I2 is equal to your I1, I2 here I am writing that your I2 is equal to I1 dash plus I1. Now, voltage across this is V1 and here it is V2. Similarly, another capacitors is here, but I am making only for this one. So, I2 is equal to what we are writing, I2 is equal to omega C into V2, because voltage across this is V2. So, is equal to I1 dash, I1 dash is G omega into 0.1 C into your V1, because this point same, this is cross arm this tower. So, it is voltage is V1. So, this is V1 plus this is the voltage across this first unit is V1. So, it is omega C V1. If you is equal to that means is equal to, if you take omega common, it will be your this one I am writing first C V1 plus 0.1 your C V1, right. So, just you apply your KCL at every point P Q R. So, if you do so, so you will get at junction P, that omega C V2 is equal to omega common this one. So, V2 is equal to 1 point V1, this is equation 1, right. Similarly, if you apply at Q and R and so on, please do yourself, I have done it here, right. Then you can write at junction Q omega C V3 will be omega C V2 plus 0.1 C V1 plus V2, because as soon as you will apply for Q, so this across this voltage will be this one V1 plus V2, That is why we are writing that's why we are writing in straightforward writing omega C V3 is equal to omega C V2 plus 0.1 C in bracket V1 plus V2. That means simplifying V3 will be 1.31 V1, right. This will be your equation 2. Now, question is that V3 we are writing V1 means this expression of V2 you substitute here, then only you will get 1.31 directly I have written here. So, please substitute V2 is equal to 1 point V1 here itself, and then you simplify, you will get V3 is equal to in terms of V1 1.3 V1. Similarly, at junction R if you apply, then omega C V4 will be that omega C V4 will be at R, omega C V4 will be your this one omega C V3 plus this voltage and this voltage, this means this voltage V1 plus V2 plus V3. So, it will be your omega C V4 is equal to omega in bracket C V3 plus 0.1 C V1 plus V2 plus V3. Again here if the expression of V3 as well as V2 both you substitute here, V2 is equal to 1.1 V1 and V3 is equal to 1.31 V1, you substitute here. If you substitute, you will get V4 is equal to 1.651 V1, this is equation 3. Therefore, when total voltage is given, that line to line voltage actually if nothing is mentioned means it is a line to line voltage, you know that, and total voltage is 66 kV. That means V1 plus V2 plus V3 plus V4 is equal to 66 by your what you call root 3, because you have to make per phase. So, V1 plus V2 plus V3 plus V4 is equal to 66 by root 3 kV. Now, what you do in this expression, you substitute V2 is equal to 1 point V1, you substitute V3 is equal to 1.3 V1 and you substitute V4 is equal to 1.651 V1, all you substitute and simplify. You will get V1 into 1 plus 1.1 plus 1.31 plus 1.651 is equal to 38.1 kV, 66 by root 3 is equal to 38.1 kV. Therefore, V1 is equal to 7.53 kV. V 2 is equal to 8.28 kV, V 3 is equal to 9.86 kV and V 4 is 12.43 kV. That means, I told you that your units which is nearer to the line have higher voltage trace. Suppose you have this 4 units 1, 2, 3, 4, you can see the V 4 is the maximum 12.43 and V 1 is 7.5 the lowest one, although same insulator, same metal is used. So, this is on a higher stage, the lower unit which is close to the conductor, and this has the lower voltage which is close to the tower, right. So, it has lower voltage and this has the higher voltage, and string efficiency, it is total voltage is 38.1 kV this voltage, and total number of disc is 4. So, it is N is 4 into the 12.43. So, it is 76.6% string efficiency, right. So, this is how one can calculate. I hope you have understood this numerical. Now, second one, just hold on. Example 2. In this case, I have taken 3 unit. A 3 unit insulator string is fitted with a guard ring, that is yours that capacitance grading thing, right. This guard ring. The capacitance of the link pins to metal work and guard ring can be assumed to be 15% and 5% of the capacitance of each unit. So, this is 15% of this one, this shunt capacitance, and this one is taken 5%. So, 0.05 C, 0.05 C, and this is 0.15, 0.15, 0.15 C. This is a figure for example. You have to find out the voltage distribution and string efficiency. This example, rather than mathematical derivation, directly we have taken this example. This arrangement is shown in figure example 2. So, applying KCL to different junction we have at junction P, you apply your what you call that your KCL at junction P. At this point you apply KCL. If you do so, you will get omega C V 2, because voltage across this one is V 1, voltage across this one is V 2, and voltage across this one is V 3 shown here, V 1, V 2, V 3, this shown here. So, at junction P, omega C V 2, that means this is your omega C V 2 is equal to 0.05, right, omega C V 2 plus V 3, because this voltage across this one, this is actually V 2 plus V 3, because this point and this point across this point and this point means this point and this point, that means V 2 plus V 3, that is V 2 plus V 3 voltage, right, is equal to your, we can write this one omega C V 2 plus this voltage is equal to Kirchhoff's first law only, is equal to omega C V 1, that is your here omega C V 1 plus 0.15 omega C V 1, because voltage across this is V 1, voltage at this same point. So, voltage across this is V 1. So, 0.15 omega C V 1. I repeat once again, you apply your KCL at point P. So, if you do so at this junction P, if you do so, so this current is omega C V 2, this current is entering at this point, plus this current is also entering in the point. So, 0.05 omega C, right, into V 2 plus V 3, from this point to this point, this capacitance grading actually from this point to this point, the voltage actually V 2 plus V 3. So, V 2 plus V is equal to these two current, one is here, another is here, that is omega C V 1, that is current here, this arrow direction is given omega C V 1 plus 0.15 this one omega C V 1. So, this is at junction P. If you simplify, please simplify this one, if you simplify, you will get 1.05 V 2 is equal to 1.15 V 1 minus 0.05 V 3. This is say equation 1. This is equation 1. Similarly, you at junction Q, you please apply again KCL. At junction Q, you please apply KCL. If you do so, it will be omega C, directly I am writing that omega C your V 3, right, and this current is going omega C V 3, this is omega C V 3, and this one I have written minus, means if you bring to this one, this current is entering, it will be omega C V 3 plus 0.05 your C or your omega V 3, that this actually directly taken to this side. So, please apply this current summation is equal to this current is entering, this two and these two are leaving. So, just please do it and simplify. So, you will get omega c V 3 is equal to omega c V 2 plus 0.15 omega c V 1 plus V 2 minus 0.05 omega c V. If you bring to the left hand side, it will be omega c V 3 plus this one left hand side, but directly I am writing here. So, I think it is understandable to you. So, if you simplify, you will become 1.05 V 3 is equal to 1.15 V 2 plus 0.15 V 1. That means, V 3 is equal to 1.15 upon 1.05 V 2 plus 0.15 upon 1.05, this is equation 2. So, substituting the values of V 3 from equation 2 into equation 1, you substitute here the value of V 3. So, you will get, after substitution you please make this, then you will get V 2 is equal to 1.0345 V 1, this is equation 3, right, because you have to solve for V 1, V 2, V 3, just like solving like linear equations, right. Now, again substituting this value of V 2 from equation 3 from this equation in equation 2, then you substitute in equation 2, then you will get 1.05 V 3 is equal to 1.15 into 1.0345 V 1 plus 0.5 V 1. Therefore, V 3 is equal to 1.276 V 1, this is 4. So, now it is, we know that you assume, because in this problem actually voltage is not mentioned, whether it is 66 or 132 or 220 kV, nothing is mentioned in this problem. So, what we will do, we will assume that in terms of percentage of voltage we will find out. We assume that V 1 plus V 2 plus 33 is equal to 100%, that will assume, right. That means, now V 2 and V 3 in terms of V 1 you substitute here, then V 3 we got this one in terms of V 1, and V 2 also we have got this one, V 2 also we have got in terms of this one. So, substitute here. If you substitute, it is V 1 plus 1.0345 V 1 plus 1.276 V 1 is equal to, we make 100%. That means, V 1 will be 30.2%. Similarly, V 2 will be 31.24% and V 3 will be 38.54%. Therefore, string efficiency, it will be voltage is taken in terms of percentage, it will be 100% divided by 3, because 3 discs are there, n is equal to 3 discs are there, into the highest voltage is 30, lower bottom unit voltage across the bottom unit is 38.54%. So, 38.5%, 86.5% string efficiency has improved. Look one thing, because of this capacitance grading, right, look at the voltage percent is 30.2%, this 31.24% and 38.5%, they are not equal, but V 1 and V 2 are very close, and this is this thing, but efficiency has increased. Now, there will be an exercise for you, that this is I have got 86.5%. Same problem you will solve without considering this capacitance grading. This part you will not consider, only you will consider this capacitance and this shunt capacitance, and try to find out efficiency and compare that one with 86.5. You will get, definitely you will get less than 86.5, such that because of this grading efficiency, this is an exercise for you, please you ignore that and only solve this one and try to see yourself. I have not done it for you, but you do it, and when you will do this course, when you solve it, you can mail to me, and the forum is also there you can put, right. So, this is your example 2. Next one. So, example 3, here that is suspension string has 3 units, right. So, each unit can withstand a maximum voltage of 11 kV. The capacitance of each joint and metal work is 20% of the capacitance of each disc. Find A, maximum line voltage for which the string can be used, B, string efficiency. These two you have to calculate. Now, this one that this diagram is shown for example 3, diagram is shown. So, similarly you apply at junction P that omega c V 2 is equal to omega c V 1 plus omega into 0.2 c V 1, same as before. So, you will get V 2 is equal to 1.2 V 1, right. So, this is equation 1. Similarly, at junction Q, that omega c V3, that means this one at junction Q, omega c, this one V3 is equal to, look at this diagram, it is omega c V2 plus omega into 0.2 c bracket V1 plus multiplied by V1 plus V2. So, you will get V3 is equal to 1.2 V2 plus 0.2 V1, right. So, this is equation 2. So, you from equation 1 and equation 2, you will get V3 is equal to your 1.64 V1, because here V2 is given 1.2 V1, this V2 you please substitute here, this V2 you substitute here. So, you will get V3 in terms of V1 1.64 V1, and V3 is equal to given 11 kV. So, V1 will be 11 by 1.64, so 6.7 kV, right. V2 is equal to 1.2 into 6.7, so 8.04 kV, and your V3 your V1 plus maximum line to neutral voltage V1 plus V2 plus V3. So, it will become 25.74 kV, right. So, V1 you have got 6.71 and V2 you got 8.04, and V3 I have not calculated here, you their V3 is given, sorry, 11 kV it is given, right. So, V1 plus V2 plus V3, because in the problem it is given that maximum line voltage for which the string can be used, and you have to find string efficiency, and this is given that each unit can withstand a maximum voltage of 11 kV. So, V3 is taken, this V3 is taken your maximum, because the lower unit near the line will take the maximum voltage, it has, that is why V3 actually taken as 11 kV. So, total is 25.74 kV. Therefore, maximum line to line voltage will be root 3 into 25.74, right. So, it is 44.5 kV. Therefore, string efficiency 25.74, number of disc is 3. So, 3 into 11, that maximum allowable limit 11 kV, that is the lower unit voltage, that is that your V3 is 11 kV, it is taken, right. So, it will be 78%. So, string efficiency will be 78%. Okay, thank you, again we will be back.